Welcome back to the 17th part of Debugging at Scale, where we go deep into the Unix kernel and come back to tell the story. The debugger is the central piece of the debugging experience, but it's only one part of it. We sometimes need to step outside of the comforting embrace of the IDE to reproduce or track an issue. In this module, we'll review some tools you might find useful for these cases. I'm focusing on tools that are 100% debugging tools and not those that are useful for development testing. Tools like curl or JQ are remarkably useful. You can and should use them while debugging, but you probably used them while building and testing the feature. So you would already be familiar with them and should have some sense of what they do. This chapter focuses on tools that you would mostly reach for when debugging. Back in 2004, I first heard about dtrace while working at Sun Microsystems. It became all the rage in the hallways as it was an innovation that Sun was promoting. dtrace was later ported into macOS 10. It originated on Solaris. Today, there are ports on Windows and Linux as well. dtrace is a powerful low-level dynamic tracing framework, but that's just another superlative. And if you never use such a tool and don't have a background in system programming, you might be feeling a bit confused. What the hell does it do? Well, everything. Do you want to know which files a process opened? Do you want to know who invoked a kernel API and get a stack trace to the caller? Do you want to know why a process died? Do you want to know how much CPU time is spent on an operation? dtrace can answer all of these and so much more. You might think that dtrace is one of those tools that will destroy your CPU completely. But here's the killer feature. It's fast enough to run in production with minimal to no performance impact. It was revolutionary when it was launched almost 2 decades ago, and it's still the case to this day. dtrace needs deep kernel support to work. This is possible on Linux, but requires a special build, so most Linux distributions don't ship with dtrace. This is mostly a licensing issue. However, dtrace is available in macOS and Windows. I use the Mac version here. We will discuss strace in the next video. It is very different, but has the word trace in the name. On a Mac, dtrace conflicts with System Integrity Protection, which is a security feature that blocks some interaction between processes, among other things. Under normal circumstances, this would be great. But if you want to run dtrace, this would be a problem. Save your data. This tool can easily crash your machine, and enabling it requires disabling important security facilities on macOS. So if you decide to enable dtrace, make sure you have a recent backup and know what you're doing. To disable the system integrity protection, we can boot to recovery mode. You can do this on Intel Macs by holding the Command R keys on boot. On an ARM Mac, we just long press the power button. Then in recovery mode terminal, we issue the command csrutil disable. Upon reboot, dtrace should work as expected. Note, you can optionally use csrutil enable -- without dtrace. However, this might not work reliably for commands that rely on dtrace. If you wish to re-enable integrity protection, follow the same instructions, but instead of csrutil disable, use csrutil enable. As I mentioned before, dtrace is a very powerful tool. There are whole books written about it. It has its own programming language based on C syntax that you can use to build elaborate logic. This is an example of what you can do with raw dtrace and its underlying language. Let's go over the command since it's pretty sophisticated. First, we have sudo. If you don't come from a Unix or Linux background, this essentially means the following will run as root or as a super user. Dtrace needs system-level access to perform its magic. A dtrace script binds to a probe. Our kernel is instrumented with hooks that match various callbacks. Dtrace connects to these hooks and can perform interesting tasks when these hooks are triggered. They have a naming convention of provider module function name. In this case, the provider is a system call in both cases. No module, we grab the write and send to entries. So when someone tries to write or send to, the following code will trigger. That would be pretty intense and can crash the system, as these things happen a lot, which is why we restrict the process ID to the specific target. This means the code will only trigger for the PID passed to us in the command line. We pass the process ID here. In this case, I used 9999 for clarity, but we could obviously would actually need the actual process ID. The rest of the code is a standard C-style printf command. If you're familiar with C, this should be instantly familiar. If not, then printf is a command that accepts an arbitrary set of arguments, the first of which is a string representing the output. I can write here hello world and be done with it. But I can also insert variables. In this case, I expect 3 arguments: a number, which I will print surrounded by brackets, followed by 2 strings. This is the number and the 2 strings. The process ID is the first. It's a number. It will be printed surrounded by brackets. It's followed by the probe function name and then by the first argument to the probe function name. This is a very powerful tool, but it has a couple of problems, the biggest of which is how complicated this whole thing is. I can read it, but writing these sort of scripts is hard. As luck would have it, we have a simple solution to the inherent complexity of dtrace. Man pages aren't always helpful, but in this case, they are very useful. We can run man-k dtrace and it prints out all the commands that are based on dtrace. There are a lot of them. Think of them as ready-made recipes that we can use to implement all sorts of cool capabilities. It's worth your time going over this list to realize what you can do here. The full list is very long, and this tool alone warrants its own book. Let's say you're facing elevated disk write issues that are causing the performance of your application to degrade. But is it your app at fault or some other app? Try read write by PID. It will print out the reads and writes to the disk. In this sample output that I cut down for clarity, it can help you see which process is responsible for all the writes or reads. In this case, we can see that the security software Sentinel is holding performance down. Let's say you can also use bytesize.d to get more specific results on the number of bytes written and distribution. That's pretty high level though. what if you want specific file names, processor names, etc.? We can use iOS Snoop to see the I/O events as they occur. The iOS Snoop -a command produces output like this, where we can see every I/O operation from every process as they occur and can understand exactly what is going on inside a binary process. This lets us debug the behavior of an app without access to its source code. Imagine what you can do if you know what the app is supposed to do and have access to the code. There's so much more we can do with dtrace and the supporting tools. In fact, there's so much I just can't possibly cover everything. But searching the web for what you need to find out and dtrace can often point you in the right direction. In the next video, we'll delve into a far simpler tool, strace. Unlike its distant cousin, it works with Linux out of the box. If you have any questions, please use the Slack channel to ask them. Thank you.